is Amirhossein Ghaderi. He's a postdoctoral researcher at York University and is working with Doug Crawford. And his talk is titled Functional Brain Network for Perisaccadic Visual Processing, Evidence from High-Resolution EEG and Graph Theory Analysis. So the stage is yours.
Thank you. Hi, everyone. Thanks for attending to my presentation. Here, I want to talk about a functional brain network that is involved in perisaccadic visual processing. And we use high-resolution EEG and graph theory analysis approach for analyzing the EEG data. So, for the several brain regions are involved in perisaccadic perception and processing, including posterior parietal cortex, supplementary motor area, and frontal eye field. And because we have a distributed brain regions that are involved in this function, we can say that a network is involved, but nobody look at the whole network that is involved in perisaccadic perception. And here we are going to use the graph theory analysis to investigate this network. First, I should talk about the method. We had a psychophysics task. We presented one stimulus repeatedly, and after that we presented a novel stimulus, and the novel one is now we name it test stimulus. And finally we asked them to judge about the duration of the test stimulus, and in this paradigm we had two conditions. One condition is fixation task and another condition is saccade task. Everything in saccade task is similar to fixation, but we ask participant to perform a saccade 100 milliseconds before the presentation of test stimulus. And exactly during the presentation during the saccade or perisaccadic interval, as you can see here in the figure here, this time is known as a perisaccadic duration. And during this interval, we analyze the EEG by source localization using the LORETA. And after that, we perform connectivity analysis to find the whole brain network. And you can see some details about the EEG and participant here. So we found this network. Actually, this is the difference between the saccade and fixation. And we found these connectivities in different frequency bands. And here, the first result, we found some brain regions that are involved significantly different in the saccade versus fixation. In the alpha band, we find inferior parietal cortex, Brodmann area number 39, and temporal pole, Brodmann area number 38, are playing the role of hubs in the network. And in the beta network, we find Brodmann area 8, that is actually the frontal eye field is involved in the saccade as the hubs. So, but other result, first we look at the clustering coefficient of the network, and clustering coefficient in a network is related to the segregation and local processing in the network. And we find that in all frequency bands, we have higher values of clustering coefficient in saccade versus fixation. The second measure that we investigated was efficiency or global efficiency that is related to integration in the network, and same as clustering coefficient, we found increased activity for that. And then we can say that the network during the saccade is more integrated and more segregated. After that, we look at the energy of the network. Again, we found the increased value during the saccade in all frequency bands. So we can say that the network in the saccade is more synchronized in comparison to the fixation. And finally, we look at the entropy of the network. And again, we find increased activity, increased entropy of the network during the saccade. So we have more complex network in the saccade condition. So this results suggest a specific functional brain network that is involved in perisaccadic interval with high level of integration, segregation, synchronizability, and complexity. And this brain network can prepare a neural mechanism for very fast information integration in the perisaccadic interval. And in the network level, this mechanism can be used to fill the gap of information during saccade by merging the information from the pre- and post-saccadic visual fields. At the end, I should say thanks to my co-authors, Dr. John Douglas Crawford and Dr. Matthias Neymer, and all of my colleagues in Dr. Crawford's lab. And thank you for attending.
Thank you very much, Amirhossein. It was really a very nice talk. Thanks a lot. So in the meantime, you can just post your questions, or if you want to ask, just let us know. I have one question. I mean, maybe it might be too broad, actually. But you were saying that these saccades were, so there was increased entropy, integration, segregation, synchronization, right? So what does this actually suggest?
So as you know, during the saccade, we should integrate the information from the one fixation point and another fixation point. And to this aim, brain need to integrate the information very fast. Then technically in the network level, we need very fast information processing to merge the previous data and post data. And we find this network actually has these properties. It is higher, it is more segregated, more integrated, more synchronized, and actually it is very complex because it needs to merge the information from the post and pre, and then it is very fast network, very optimized and fast network. So actually this is the goal of this research, yeah.
Mm-hmm. Thank you, thanks.
I have a question. I have a question. So, so you recorded from both the left and the right hemisphere. So, is there any modulation on the parameters that you measure, like the entropy, the connectivity, the energy, depending on where the saccade is going to be, or where does it start?
So we in the psychology in the psychophysics paradigm, we had first we had vertical saccade to the left and to the right, and when we compared the saccades to the left and saccade to the right, we didn't see any significant change in the network properties, and actually the degree of the saccade was just 10 degree, but I am not sure if we have, for example, the a bigger saccade or maybe a vertical, a horizontal, a horizontal saccade. I'm not sure about the other type of the saccade, but in this stage, we didn't say that there's any difference between saccade to the left or to the right.
I see, and this is on the binocular field, right? On the where you can see with both eyes.
Yeah, and all of the participants was first was fixed at the center of the screen, and then we asked them to perform a saccade to the left or to the right, as you can see here.
Okay. Oh yeah. Okay. Thank you.
So there is a question from YouTube, and it's from Daniel Kramer. And the question is this suggesting that the brain operates with such kind of networks to solve tasks and or to make decisions, and that they get implemented by the neurons itself?
So here we are talking about, we are not talking about, for example, decision making at all. And the duration that we investigated was just in the perisaccadic interval before decision making, before the, for example, a further cognitive function. Here is just, this duration is related to when we are preparing to perform a saccade. It's not yet before the saccade execution. Even. And but I am not sure, maybe we can test same methodology, EEG and graph theory analysis, and we can investigate same measures to, for example, find a network that is involving decision making, and this thing is related to the EEG, and we know that EEG is related to the neural activity in a very, very big scale. And I am not sure about the result when we are looking at just a single neuron or just, a small network of the neurons. But we can, technically, we can use the same approach for different data. Even fMRI or electrophysiology is recorded.
Oh, sorry, I was on mute. So I just thanked for the questions. And I would like to thank you, Amirhossein, again, for the very nice talk. We can move on to our next speaker.